Well, go ahead.
Hey, welcome everybody. This is Mark. Daryl's here. Hey, Daryl, how you doing?
Hi, Mark. How are you?
And we're both say hello to all of you. We're trying to go through. We actually I was outside earlier and started up everything. Got the dome and the telescope all running, and as clear as beautiful as anything. I looked where the comet was. Actually, had the telescope go to where the comet was, and it was looking into the trees yet. So we have a few more days before the comet will be above the trees for us to see. But man, I'm really looking forward to it. It's going to be beautiful when we do finally get a chance to see it. So that said, we are going to be looking at Jupiter and Saturn tonight, as well as some other astronomical objects. But when I went out just a few minutes ago, I noticed that there are clouds where there were never any clouds. Suddenly the sky was full of them. So I have to start up the all sky cam and get an idea of what we have for clouds, okay? But until then, let me just bring us to our live current view, and you can see from this live view here that we have a reddish sky that seems to be changing. You see some modeling that changes. That's actually the clouds as they're moving past the telescope's view, or through the view. And we will be moving, well, actually the telescope is already looking at Jupiter right now. So we can't see it because there's a thick cloud bank blocking Jupiter from us at the moment. But that hopefully will pass, because it looks like it's going to. So that all said, welcome to SkyTour LiveStream for today, July 13th, 2020. I'm looking forward to a good evening with you guys, and hopefully we'll be able to look at some very nice objects, some really interesting objects. I really enjoy all of you coming out to see this, and I'm hopeful that we'll be able to pick up some gorgeous views of the comet in coming days. Right now I'm going to start up our all sky camera, and I get the all sky running. We will then look at the overall view of the sky. So we're going to go into continuous mode and auto save the image and apply the processing, and we're going to do this as a we'll start off with a 30-second image. All right, and we'll say take the photo, and now we'll come back to that in a moment to see what it looks like out there. I want to say hello to Marianne. Rob is here. Daryl is right next to me right here in the studio, but you can't really tell because he's only about 1,000 or 1,400 miles from me, but you'd never know
like
it.
that.
Yeah. And Papa Tom is here, and Daisy and Zoe are here, and Tara is here. Dandelier, who is not from Danbury but from Bristol, and we have P&K. Guess who that is? Yeah, that's Keith. Is here, and we have let's see, we've got a few Farbas here as well, and Samantha Peebles, and Karen is here. Karen Belmont, what's up? And we're trying to find the comet tonight, but unfortunately it's in the trees already. Hello, Monica Hart is also here. Cypher 2, and we're trying to find other objects until the comet will be higher in the sky in coming days, and so those coming days will bring the comet high enough so that it'll be beautiful and visible to our telescope. Right now it's low. In fact, when I actually pointed the telescope to it, just as I opened the observatory, that the telescope is already looking at trees. So it's kind of low. It just started into the evening sky, and basically the 15th is when we can actually start in earnest to look for it, and then it'll be a little bit more visible. Hello there, Justin T. What's going on? Kathy Bernasek is here. You guys are fantastic. I love that you come out. Andy Morrow's here. Canada Boy CND is here. You guys are very much appreciated here. So that said, let's hope that the skies will clear. And Trish D, thank you for joining us. I'm waiting now. Let's go back and see what our all sky looks like. Okay, see, now that's okay. right? Well, this is the area where Jupiter and Saturn are, okay? This is the coming area. This is the area where they came from, so they're going this way. So it looks like we have clear behind it, see? So that's going that way, so we're good. We just have to wait it out. And the fact that the clouds look so sharp is in part because it's only a 30-second image, but unfortunately it's also because they're not moving very fast, and so we end up having to wait for them. But we will wait, and when they're gone, then we will have our views back. Terry Groff, hello. Bobby Burgess, hello. Yeah. So I'm very pleased that our sky is clearing, and I want to thank Daryl for joining me tonight.
Sure.
Did you hear from Amanda?
I did. She just got your message and my message, and she has a bit of a headache at the moment. She may join us in a while.
Okay.
She said she might try, see how she feels.
Let's all think very, very strongly to get rid of Amanda's headache, shall we?
Oh, yeah.
Yeah.
Everything's better with Amanda.
Yep. Davey Dreamer's here. Hello, Davey. And Ha is here as well. Bob Harless, thanks for joining us. We're actually just waiting out the clouds here. As you'll see, this is our all sky cam. This is a camera that's going to be set up in Arizona as well. Let me give you an update on Arizona. I had scheduled a trip with, in fact, Marianne was helping coordinate that for me here, Marianne in chat. And I was supposed to leave here on, today, to go out to Arizona, but we bumped it up to the 24th because of COVID, and it looks now like we are going to have to bump that to the 1st of August or so, because of the fact that COVID is causing issues. So I'm really anxious, as you can imagine, to do this. I don't want to wait any longer, but I know that I have to be safe about it, So we're just waiting for these clouds, and as soon as we see a bright object down here, then we will know that we have Jupiter back in our sights, because it's going to be in here. So
is there a porch light on the front of your house?
Actually, that's my youngest son, Hunter. That's not a porch light. That's actually an upper round window.
Oh.
It's a big round window that's at the peak of the roof in the house. That's in his room. It only affects his camera. It doesn't affect the telescope at all.
Okay.
Or I would have shot it out with a BB gun, even though it's my own house.
There you go.
Yep.
We have the technology.
Absolutely. Yeah. So we're just waiting for the clouds here. It's going to be promising, hopefully, shortly. Let me actually try an 8-second exposure and see if I can catch anything just peeking through the clouds yet. Yeah, no. Not yet. In fact, I may... Let me just go look at what the telescope is seeing. Just a moment here. One moment. Daryl dropped on me. Wrong button again?
Wrong button again. Sorry. I'm really spazzing out tonight.
This is Daryl. Wrong button, Mason. Hey, you know what?
There you go.
That's funny. That could be it. That could be your new nickname.
Could you share your screen again?
I could.
You could.
Yeah.
I'm sorry. I don't know what's wrong with me tonight.
Nothing. You're all right. There we go. So there
Thank
we
you.
are. Hey there, Chris David O'Reilly. How you doing? Okay, let me
Thank you, huh?
yeah.
I think I was trying to mute and I hit the red button instead of the white button. And yeah, that's Skype for you.
Yeah. They're nice and close to each other, so you can easily miss them.
Yeah. I guess I could try the one up on the top.
Yeah, that's true.
No, that didn't work either.
All right, let's let me try.
Hello, Ronald.
Ronald is here. ERRT Radio. Art. We're waiting for clouds, guys. And in case you're wondering where they are, well, you can see. Yeah, see, we're starting to get clarity here, and we're actually looking down here right now. So obviously, this is the last thing to clear. So this is just the way it is, right? Always happens that way.
Yeah, vagaries of the weather.
Mm-hmm.
I've been up really late some nights, and I've dropped in on Take Back Space a couple of times, and he has had some exceptional seeing down there some nights. He's looked at Jupiter and Saturn and the moon,
That's
and
great.
gotten some great looks at the planets lately.
Cool.
While we're waiting, would you care to talk about what you and I discussed in private some days ago? About Jupiter and Saturn, and they're moving apart instead of moving together?
Yeah, actually, while I'm determining where the telescope is pointing here, why don't you tell people about that? The conjunction and opposition situation with Jupiter.
Okay, well, if you watch the sky regular, you may have noticed Jupiter and Saturn are together down in the south. They're in eastern Sagittarius, I guess, or in the border between Sagittarius and Capricorn. And Jupiter has been catching up with Saturn night by night for like a year now. Closer and closer, night by night. But watching closely, I've noticed lately that Jupiter is actually moving away from Saturn again. And Mark and I discussed this, and Mark knew it. He guessed it instantly. Jupiter is at opposition tonight or tomorrow night, depending on who you listen to. That is when Jupiter, the Earth, and the Sun make a straight line in space, which is called syzygy, S-Y-Z-Y-G-Y, one of my favorite words. And that basically is when Jupiter is closest to us for the year. If you draw a line from the Sun out through Earth, that line will intersect or almost intersect the planet Jupiter. And that means we're all on the same side of the Sun. And we're closest pretty much for the year, except maybe for the fact that since the planets all move in elliptical orbits, sometimes the actual closest day can be a day or two on either side of opposition. But anyway, as we have come into opposition, Jupiter started moving away from Saturn. And this is what puzzled people back in the good old days, especially before Copernicus, because people watch the sky every night. Some people watch it very closely. And they noted in the past that, the planets move, their direct motion across the sky is from west to east. But sometimes they would see the planets start to move backwards in the sky. It's called retrograde motion, and it starts moving east to west in the sky. And in effect, if they can plot that against the sky night by night, it makes a little loop in the sky before it starts going east to west or west to east again. In the days of the Clockwork Universe, they tried to explain this. They called them epicycles. And when they built like orreries or little solar system models, some people actually built in a little gearing that would make the planet move backwards for a while to try to duplicate that effect. But what we're seeing, you may have heard me say before that if you could imagine by analogy here, that if we're on the big interstate highway of the solar system and we're making a big sweeping left-hand turn with the sun at the center of the curve, and Jupiter is out in the outside lane and Saturn is in the next lane farther out than Jupiter even, that as we catch up with Jupiter moving toward opposition, Jupiter's position in the sky will appear to move backwards. That's just like if you're looking at somebody in the outside lane. At first you see them ahead of you and they're moving forward, but as you catch up with them, you will see that object, that car, that planet in the outside lane start to drift backwards compared to the background sky or the background trees and service stations and stuff like that. Well, it's happening now because Jupiter is at or very close to opposition. Jupiter again is at opposition tonight or tomorrow night, depending who you talk to. Saturn is at opposition just 6 days later on the evening of the 20th. And actually, both planets are making that backwards loop in the sky right now. But Saturn being farther away, it has a smaller loop. Jupiter being closer is making a bigger loop in the sky. So in effect, Jupiter has been moving away from Saturn as part of both of them moving to opposition. Here, a little after opposition, it will start moving west to east again in proper direct motion. And when I posited all this to Mark the other night, Mark's one-word answer was, sure, it's parallax. Okay, Mark has described parallax before. And that's exactly what it is. It's seeing a foreground object shift against the stellar background in the sky. And that's all because all three of us are, well, both of us, the Earth and Jupiter are moving, but Earth is moving faster than Jupiter, so in effect we see it moving backwards in the sky.
Yep.
So yay, Mark.
No, that's okay. I mean, these are elements of astronomy that you end up, becoming well versed with. Another way to basically see it is to understand this parallax thing is if you hold your finger out, hold your finger up in the air, and you hold it out at arm's length against something that you can see in the background, like a set of trees or a forest or your wall. And if you close one eye and then you look at your finger, it'll be against a certain number of trees or wall elements in the background. But then if you open your other eye and close the eye, alternate your eyes, in other words, you'll see the finger jumping between two positions. That angle, that distance it moves, is called the parallax angle. And if you imagine your finger is some of the nearer stars to us, and the wall or the forest are the farther stars, you can see how we could figure out the distance to these nearest stars very accurately by being able to measure very accurately this shift against the background of further stars. And that's the parallax thing. I worked in a parallax program at an observatory where we studied nearby stars, and we had parallax for many, many, many stars that we would go over and over and over and get new and refined data for all the time. It was really quite fascinating, and it worked very well. It was a really interesting project.
Yeah, and I know you've explained before what a parsec is, that short for parallax arc second. And what that is parallax arc second out in the sky, out in space. If you were to project the Earth-Sun distance out in space, 93 million miles, that angular distance it covers would get smaller and smaller the farther out you go until you're 3.26 light years away, when 93 million miles would equal 1 arc second in the sky.
It's a good explanation.
That's 1/60th of a minute, arc minute, 1/60th of a degree, or 1/3600th of a degree. So it's the distance between the Earth and the Sun pushed out into space, 3.26 light years, and that makes 1 arc second in the sky.
Yep.
And that's why Han Solo was wrong in the first in Star Wars, that He said they did the Kessel run in 12 parsecs.
Exactly, which is silly.
Yeah, it's a measurement of distance, not a measurement of time.
That's correct. I think that's very funny. Very, very funny. Okay, let me go here. I see we've got some clear skies. So let me bring Jupiter back in here. I'm not sure where it decided to go, but we're going to grab it. Okay, we're going to a beta. And then from there, we're going to make a little hop over to Jupiter. So it gets centered, and then Jupiter will be brought in. There we go. Ta-da! And there are our Galilean satellites.
Just a second, I'll tell you which one is which.
Yeah, good. Okay. You'll notice there's a little bit of a yellowish color. The reason that Jupiter looks yellowish tonight is precisely because it's low in the sky. It's really kind of low. We're looking at it kind of low at the horizon. How low? Well, if we go check out our setup here in our planetarium view, we can actually see that we're looking at, let's see, where is it here? You can see that it's near the trees, near the horizon. This is actually, if you remember, this is actually my horizon. So we're really low right now. Yeah, we are only, is it 20 degrees? What is that? 15 degrees. It's 15 degrees above the horizon. So we're still we're looking through a thicker atmosphere. And I believe also that we have a problem, not a problem, but we have to also focus. So I'm going to bring Jupiter and its satellites down into our focus zone. Okay, there goes Callisto, and we're going to head eastward now and bring in Jupiter. Okay, and let's focus now. Get these focused up.
So, like, you already know which ones they are.
Well, I know the Callisto's that outermost one.
Yeah, on the right.
And I think Io is the one that's right here.
That's Ganymede.
Oh, is it Ganymede? Then that means that
Io's farthest on the left, then Ganymede.
And then this must be Europa.
Right is Europa, and Callisto is far off on the right.
Yeah, I was just guessing anyway. I wasn't sure. All right, now let's take the ISO down. Bring it down to a very low, and that means the ISO is the sensitivity of the telescope. We're going to go down to 50 ISO. So get to 64 and then 50. Okay, and now we're going to shorten up our exposure. And as we do, you'll start to see the Jupiter's Galilean satellites disappear, because necessarily, in order to see any detail on Jupiter, we need to get rid of the Galilean satellites because of their brightness. So let's just take a 1/50th of a second exposure here, just to get an idea how it looks. Now let's go over here. First of all, we want to I'm going to rotate it So let's do this. Let me bring it in.
Interestingly, the Great Red Spot will become visible in about 3 hours or so.
Yeah.
And Io and Ganymede will have traded places.
Oh, very cool. Well, there you go. You can actually see we have some cloud bands. They look vertical right now. And that's only because of the fact that I rotated Jupiter. If we go back the other way and pull out this location, we can come back. Let's see. Here we go. Okay. And that's in the murk. You sure the great red spot is not visible? It looks like it's right there.
Unless my... let me check.
Sure. You could be right. Let me just go take another photo. For a moment. And let's just bring it a little brighter. 2 stops brighter. 25th of a second. What do we got? Let's see. Okay, we can see the hint of the moons here and here. That still looks like it might be the red spot. Terrible.
Let's see. I'm referring to JavaScript Jupiter, and I know it's off a little sometimes. It does show a dark feature in that upper belt. According to this, the red spot will be in the lower belt, as you see in your image.
Yeah.
It does show a dark feature there, though.
Yeah. And Farvid, answer your question. Not at all. Not at all. You're one of our greatest contributors, man. I love you. I don't have any problem with that. I really enjoy your company. I've just been consumed with trying to get this telescope to the West Coast and so forth. I am certainly very grateful for your continued presence and patronage for us out here. So I'm very excited that you come out and hang out with us. Heck, I actually, I'm waiting for you to tell me how that telescope works, because I remember consulting with you on that telescope to get you that telescope. I think that's a really good scope. I can't wait to hear what you're doing with it. Yeah, so I definitely see, I have this exposure set up so we can see Ganymede here and Io here. And Europa is going to be out here. And interestingly, Europa sometimes isn't as visible, but it's one of the brighter of the moons. And the reason it's not as visible is because it's smaller in diameter. So it's kind of interesting. But it's kind of, if you look at it, we're seeing it kind of in this sunset view, don't we? See it, and so that's because it's reflecting light of the sun anyway. But that's the light we're seeing from it. But we're seeing it through a lot of atmosphere because it's low in the sky. Again, recall our view. Okay, Jupiter is really close to the horizon here. It's only 15 degrees above the horizon right now. And being that it's only 15 degrees above the horizon, it's looking through a slant of atmosphere. It's more atmosphere in that direction. All right, the atmosphere's thicker out there. So what that does is that causes the blue light in the spectrum of the sun's spectrum to be more scattered because when the regular sunlight hits the atmosphere, it has all the colors: red, orange, yellow, green, blue, indigo, and violet in it. But the blue light in particular, because it's higher energy, all right, and the indigo and violet light, these get absorbed and immediately re-emitted. And it doesn't matter which direction it gets emitted in. To the molecules in the atmosphere. So that emission causes you to see a blue sky. That's why the sky is blue.
Rayleigh scattering.
That's right. It's Rayleigh scattering. And there's another kind of scattering. You might say, well, wait a minute. How come clouds are white then? If you think about this, when a cloud is hit by the sunlight, obviously the cloud also is reflecting the sun's light, but it's also scattering as well. But clouds look white, or gray, but they look predominantly white. That's another kind of scattering. And it has to do with the way the water molecules work versus nitrogen molecules and oxygen molecules. And the water molecules do something interesting, and that is that they absorb all the frequencies of light and emit all the frequencies of light. So what happens is clouds are not selective about the colors that they re-emit. They re-emit all of them. And what are all of the colors in the spectrum? What does that equal to? White. The same color that came in from the sun. So clouds look white because they are doing what's called Compton, Compton scattering, as opposed to this Rayleigh scattering, which is a specific higher energy scattering of higher energy light photons from the sun, the higher energy wavelengths from the sun. So it's pretty interesting. I just thought that that would be an interesting thing to talk about. Now let's go back to Jupiter here and see if we can grab another view, and let's center it up a little bit more. We'll go west a little bit, and let me see. Let's grab the moons. So we're going to go up to a little bit longer. Okay, there you go. And so these are the moons that we're doing now with a 2-second photo. Okay, and you say, well, where are they? Well, they're actually going to be right here. Okay, so here are the moons, and again they're low. But as Daryl pointed out, this little guy right here is Ganymede. All right, now Ganymede is the next farthest in from Callisto. It's like, you have Io, you have Europa, Ganymede, and Callisto. That's the order of distance from Jupiter that they are. But how come Ganymede looks like it's right here? Well, the answer to that question is that Ganymede is actually just passing around Jupiter. Okay, and as it's passing around Jupiter, either in about to pass in the front or in the back, Jupiter, it'll look like it's close to Jupiter, but it's not. It's really the same distance. It's just much further away from Jupiter, because it looks closer only because of this fact that it's superimposed. The orbits are big circular planes. They go like this: big circular plane. Okay, big circular plane. Okay, Io's a circular plane, and then Ganymede's is second biggest next to Callisto.
I believe Ganymede just came out from behind Jupiter.
That would be here.
Yep.
Yeah.
So it's actually behind Jupiter. It's just
Okay.
because we're looking close to the plane of the moon's orbit, so they look like they're on the line.
Yep.
And again, if we're around 3 hours from now, this is the dance of the Galilean moons. We will see that Ganymede and Io have traded places.
That's right. This is Ganymede, and this is Io. And Kathy, I have turned on the music. Thank you very much for letting me know. Thank you very much. Unfortunately, I can't hear the music right now. There's a little glitch in the software, so I only see the levels, the sound levels. I don't hear the music at the moment. I'd like to say it's all Daryl's fault, but I can't in good conscience blame him for something that isn't his fault.
Oh, go ahead. I got
Nonsense.
big shoulders.
Nonsense.
My belly's getting smaller, though.
You know what? That's funny you mentioned that, because I've been on an active crusade to just drink water all day long and then eat a regular meal at night, and I haven't had any problem doing that. And I am actually, as of this morning, I was 179 pounds.
Wow, good for you.
I started at almost 200, and just by drinking water, it's been just about a month and a half, and I've dropped almost 20 pounds. This is because this is weight that your body just doesn't want, and it will just melt away. And I've been exercising and doing all the things before that you do, and I am like 4 pounds from my high school weight right now. 4 pounds. Like, wow. You know? Pretty
The
cool.
end of ski season, 1984, I weighed 164 pounds.
Wow.
And I still have a ways to go to get there. I'm a little bit behind you, but I am still losing weight.
Fantastic. I'm very, very proud of you, man.
Yeah.
Yeah.
I used to be so pretty.
Yeah. I want to say hello to Heidi Gadd. Hello, Heidi. How are you? Heidi's amazing, you guys. If you ever... she is actually a violinist. She's a concert violinist. Actually, Heidi, put a link in the chat for people to check you out, okay? Because you've been very helpful to me in helping me get a presence on Instagram and Twitter. Well, I've had those presences, but I just haven't used them until Heidi came along and slapped me around and said, do this, do this, do this. And now I'm trying to do those things to help get the word out about SkyTour LiveStream. And thanks to her, we're gaining a lot of new subscribers. After the lunar eclipse, we went up almost 665, 670 subscribers almost overnight. And part of that was due to Heidi and her influence as well. So I want to thank her publicly for that. Because, the whole point is, if you do something cool, you're never doing it on your own. It's never just you. You got a lot of people behind you. I've got Daryl here. I've got Amanda who helps us, so that makes a lot of sense, So I really think that you gotta basically be humble about it and give the people that have helped you along the way their credit. And that's what I'm doing. So I just want to publicly say, and Heidi, make sure you put a link in because I want people to know who you are, okay? And what
Can she put in a link if she's not a mod?
Sure. I mean, she can just type it in. I don't see why she can't. Is that true?
I thought that was the case.
Right. Okay. All right. Well, let's see here. Let me see if I can help her out with that. Heidi, I'm sorry if I misspoke here, but let me just do that. Okay. Now you can put in a link, Heidi. She's been very, very helpful to me, so I wanted to make sure that now she's a mod. So and she's right. It takes a village. That's right. And anyone who thinks that they built the entire village on their own, that's the first step in you falling down that hill. Yeah. So I gave Heidi a wrench so she can now put in her link if she likes. And you have a wrench too, Daryl. Don't worry, I gave you a wrench a long time ago.
Yep. I didn't even ask for it. I didn't even know you gave me one until the next time I came to your stream.
Well, you know what? That's what happens, It's the things you don't expect that mean the most. So, very, very happy that you have been hanging around in SkyTour LiveStream and decided to take part in SkyTour Radio with us.
Well, of course. Tons of fun.
That's right. Let's see what our all sky. Oh, look at that! Our all sky is showing us that we have a clear sky. I'm going to up the exposure time. Now we're going to go to 45 seconds, and we'll do that. And now I'll be able to check those out. All right, good. So this is nice. I know, Farva, you're right. And that's actually, to be fair, you have been doing a lot for us. So I'm going to do the right thing for you two right now. There we go, Heidi. Thank you. Yep. You're not the only one that donates, Farva, but you are the only one recently that have been donating. So I do want to thank you for that as well. Okay. Hey, Carol, how are you?
Hello, Carol.
Yeah. Good job, Trish. Yeah. You know what? We should support the moderators of these channels. You know, and the people, they've got their own thing going, they got their own stuff. You know, they don't need to sit out there and talk about the benefits of some observatory. It's you know, sitting in New England and in Arizona. But when they do, you know, it's really helpful. So, you know, patronize them, give them your patronage as well, because those are good people. Those are really good people. All right, let's see.
I've never been convicted of a felony.
I'm not sure what brought that on, but great.
Convicted.
Convicted. I know. I said he's been tried.
Not me.
No.
I'm sorry. I'll shut up now.
Oh, stop! You're not saying anything silly. You're fine. Okay. Well, there's Jupiter. What it looks like right now. Yeah, and I do have. I think what I want to do is I want to alter some of the. I want to alter some of the filters, Robin. Let's see if I can do that. Set the defaults there. Yeah. Yeah, we'll see. For low in the sky, that's not so bad yet. What? Carol, you're disappearing already? See that? She found out the comet's already set and she doesn't want to be here now. Wow. I'm kidding. Carol's a sweetheart. Well, let's see now. If I go back to the all sky, we should have another view. Okay. And we have some clouds up there. Let me do a little processing here just to check things out. Let's stretch a little bit here. Oops, gotta activate it first. There we go. Okay, so there's our sky right now. This is not clouds. That is to say, water vapor clouds. These clouds here are the clouds of the Milky Way. This is the Milky Way coursing over the house here. There's the house. And you'll notice that light there is off. Oh, you can't see it because I'm in the way. Let me move out of the way. Let me get myself out of the way here.
I'll take your word for it.
All right. Maybe I can do this.
Yep.
Yeah. Now you can see. Okay. Great. All right. There we are.
There's the Big Dipper at the bottom, and if you follow the curve of the handle, you can see Arcturus is that bright star to the upper left of it.
Yeah, right there.
And if you keep following that curve, there's a Spica over toward the left-hand horizon.
Right there.
Yep.
Yep. This star here is one known as Vega. This star here, I believe, is Altair, and I believe that one's Deneb, is it not?
Negative. Deneb is the one higher up, and
this is Altair.
Deneb is the one lower down to the right.
That's Deneb. Oh, yeah, yeah.
Altair is
Okay, this is Vega, this is Deneb, and that's Altair.
Yeah.
Yeah,
and
I was looking at it.
The one right next to Altair is Terrazet.
Next to Altair?
Yep.
You mean this one?
Yep, little bitty one next to Altair.
Yep. Hey there, TP Seeker. Good to see you. Yeah, okay, well, there we go. So now we have that, and we're seeing Jupiter. Jupiter's really low in the sky, but, you know, in our all-sky camera, all right, it's right there. Okay, that's Jupiter, and that's Saturn. All right, oh, no, what's that? You want to see Saturn? Oh, okay, well, maybe we can go see a yellowy Saturn, too. What do you say to that, Daryl?
Sure.
Why not?
Saturn is kind of yellow anyway.
Saturn is kind of yellow anyway. That's correct. That is correct.
Always looked like a big fried egg to me in the eyepiece.
Yeah, that's why you need a telescope to take a picture. All right. Have you had your telescope out lately?
Negative.
Oh. There's gonna
I
be a
have
reason.
been kicking myself about that. Don't make me feel bad.
I'm not. I would never make you feel bad. I would just want to motivate you. That's all.
Oh
Okay,
yeah.
heading to Saturn, you'll see Jupiter disappear.
Yep. Specifically, see Jupiter when it's at opposition.
Yeah.
You know me. I love my old red 8-inch telescope,
Oh,
the one
yeah.
I made. But
Yeah.
I really need to drag out that Celestron, and put it through its paces.
Yes. Yes, indeed. Yep. Well, that's what happens, you know. We want to try and there's Saturn. Can't miss it. Come back. You're going the wrong way. It's alright, it'll be coming back. Yeah. Alright, so let me just pull us in here. Yep. Yeah, and this little guy is Saturn right there. You can see it's got the little rings on either side. Can't miss them. It's really nice, you know. But let's go look at it a little closer, shall we? I think it's better to check it out close up. So let me bring it in more to our view. Okay. All right.
When Galileo first saw Saturn, he didn't get it at all. His first telescope wasn't very high magnification, and it didn't have very good resolution either. He looked at Saturn and he was dumbfounded. It looked like it had ears. He couldn't make out the rings as such. All he saw was ears either side of the planet. He called them ansae, Latin for ears, I guess. A-N-S-A-E, ansae.
Yeah, that's it is kind of odd, because you don't, if you've never seen a planet with rings before, you wouldn't really know what you're looking at.
Yep.
You know? Alright, so there's Saturn with its ears. Okay. And I mean, for low in the horizon, that's actually not bad focus. You know? Doesn't look that bad for something that low in the sky. You know, we can't see Cassini's division, which is a fine dark line that goes to the middle of the rings here. We can't see that, but we are able to see the planet itself and some hints of the bands and tiny suggestion of the ring structure. So it doesn't look that bad at all. And it'll get higher in the sky too as the evening wears on, but you know, we won't be able to go incredibly long tonight. We are looking at we do have this southern sky over us right now, actually, so we should actually be able to check out some of the beautiful summer nebulae already. What do you think of that?
Sure.
Yeah. Okay.
Mark Genghis asked a question.
Sure.
Daryl or Mark, can a moon be gaseous and can a moon have rings? Then he says, or a dwarf planet. Oh golly. I guess if a moon was big enough, it could be gaseous, and I suppose a moon could have rings. Your thoughts?
Well, I guess it depends on the situation. The dynamics of the bodies that are the planet and the moons. Keep in mind that the planets and the moons as they are have taken billions of years to stabilize into their what we call resonance that they have. And you know, for instance, Jupiter's innermost moons, Io, Europa, Ganymede, and Callisto, they're in a resonance, and Io, Europa, and Ganymede are in a 1-2-4 resonance, meaning that For every 4 times Io goes around, Ganymede goes around once, and Europa twice. That's a pattern that developed over time based on their masses, their gravitational forces, the tug of Jupiter, and the grand total sum of all the forces acting on those moons. So, could a ring system survive around the moon? That's a good question. With all the things that change in a dynamic solar system, maybe not. I mean, we do know that planets have moons, okay? And effectively, moons are just rings that have kind of coalesced into objects, right? So if Io was destroyed, and if Europa was destroyed, and Callisto and Ganymede were destroyed, then Jupiter would have more ring than it does now. And it does have rings now, actually. Jupiter does have rings, and they were found actually some years ago when they were backlit, when a probe went past Jupiter and looked back through this, through the ring system that it didn't know was there toward the sun. It saw this backlit ring system, and that backlit ring system was very dark material. Now, why dark? Well, because for the same reason that when we look at comets, the nucleus of a comet is an icy body, and you immediately think it's shiny and bright. Nothing could be further from the truth. The surface of a comet is like black tar. And I know that seems odd, but it is. And the reason is because whenever you expose soil and other material like that to long-term exposure of radiation, solar radiation, interstellar radiation, when you have the objects way out in the Kuiper Belt, passing stars over billions of years will affect them with their cosmic rays and their radiation. It changes the composition on the surface, and you end up with this basically scarring in a sense, but it actually is a weathering more so. Weathering basically known as space weathering, you might say. Actually, that's a good way to put it. And it's because of solar wind and cosmic rays that this material becomes black as tar. The Churyumov-Gerasimenko Comet 67P that the Rosetta mission went to and landed on, if you remember, with the Philae lander, which got stuck in a crevice. Brilliant mission. That mission, when they found the comet, they got to the comet was actually almost black. But you'll say, wait, no, I've seen photos, it looks gray. Yes, that's right. Those are time exposures. Those are high ISO time exposures with very, very, very high power cameras, so you can actually see something. But you don't actually, you can't actually see the black. So you're not gonna see it as black. They're not gonna show it to you as black. Same thing with some of the asteroids and some of the dwarf planets out there, like Vesta and Ceres. Their surfaces are not gray like the moon. We're used to thinking that asteroids are gray like the moon. It's not true. They're very, very dark. And so we have to take longer exposures in order to show them. And when you take a long exposure of a black object, it looks gray. Let's be honest. So that's kind of what's going on there. So cometary nuclei are actually quite dark, And I'll give you an example. You look on the moon, all right, and you see the crater Aristarchus, all right. Now the crater Aristarchus on the moon, and I'm going to show you Aristarchus right now. Let me first of all, let me go back and take us to a little bit of a different thing here. Let me just do one thing here. Hold on. And we'll do... Alright, we'll do this. Okay. Alright. This is Aristarchus crater. Alright. This is a 3D print from our SLA printer. I just did this the other day. Okay, and I'm going to try and arrange this for you. Sorry, I'm gonna increase the size. I'm trying to show you a little bit about how this works to give you an idea. Okay, so it's going to be backwards too because of the way I had to show it. This is Aristarchus crater. You'll notice that it has a white material here, here, coming out of the crater. The crater is this one here, okay? All right, and you'll see this white material coming out of the crater. It shows it best there. This crater over here next to it is called Herodotus, all right? And Herodotus is 1 billion years older than Aristarchus. Aristarchus is only 450 million years old. And that white material that's coming out of Aristarchus, that white material, is white only because it hasn't been subject to the cosmic rays and solar wind as long as the other material around it on the moon. So the material is white for that reason. Over time, though, it will darken. In fact, it's that reason that we were able to help age Aristarchus crater here, right, and figure out how old it is. All right. So that's how weathering in space works. That's how space weathering works. All right. It's kind of an oddball thing, but it is how it works, and it's exactly what happens with comets as well. The surface of comets will get turned into this dark color as well, black as tar. All right. So again, this is something that happens because of the radiation. So I just thought that was something that maybe it would be good for you to know about. So any questions, let me know on that. But kind of a long drawn out answer, I think, to a question. I think wasn't that Genghis who asked the question way back when about the planets having moons and so forth?
Yeah.
Yeah. Well, again, the reason that I went down that path is because of the dynamicism of the solar system. Moons around rings around a moon might not survive. In fact, Saturn's rings are evaporating. I don't know if you're aware of that. Are you aware of that, Daryl?
Yes.
Yeah. Saturn's rings are evaporating, and it won't be long before Saturn. Now, it won't be long. It'll be millions and millions of years, but Saturn's rings are falling into the planet, and will eventually be a ringless world. And that's what's that?
Did you recently talk on SkyTour Radio, I think, about the moons of Mars, like being the remnants of a ring system or something?
We did talk about that, as a matter of fact. That everything we see in the solar system now is a snapshot in time of the current state of our solar system, but it's not a state that is constant. It's always in flux. Nothing is ever sitting still in the universe, right? So we end up finding that things like a ring system are transient. The moons of Mars, Phobos and Deimos. Okay, Phobos and Deimos look like they've been through the mill. They've been collided with, and it looks like there was a collision at some point. And so the larger objects might have, created Phobos and Deimos, and then a lot of the smaller elements ended up infalling into Mars and crashing into Mars. We see remnants of this kind of thing all the time in the solar system, but we don't recognize it. The closest thing, for instance, to a moon having rings, in a sense, is Saturn's moon Pan. You're familiar with Pan, right, Daryl?
Is that one of the shepherd moons?
Yeah, right. It doesn't pan. It has basically it's round, but it has this outside ring. It looks like a UFO. It has this ring of material around the outside,
Yes.
but it's attached to it. It has this flying saucer appearance to it.
It looks like a fried pie.
That's correct. And it looks that way because of how it formed. Again, being part of the rings, it always had this debris falling on it because those rings are in the ecliptic or along the equator of that moon. The material tended to pile up along that outside edge of the moon, and thus over time it made this really cool looking ridge that extends out into space, which is really cool. And that's really neat about Pan. if you have any questions, guys, let me know. I'm just looking at another place to go here, and there's so many choices. I gotta figure out which one we want to go to. You know me, just one more, right? Just one more thing, just one more thing. And we're only getting started, right? So I may have to move the dome if I do this, which is fine with me. I don't mind. Okay.
Hard to go wrong with M8 and then work your way up the Milky Way.
Yeah, no kidding, no kidding, no kidding. Yeah. No, and many times I get asked about the butterfly cluster. Well, here it is. It's down here. We might actually be able to see it tonight. You know?
Butterfly cluster.
Yeah.
M6 or M7?
Butterfly cluster?
I forget.
Let's find out. Butterfly cluster is M6. You're right.
Okay.
Good call. Right near Ptolemy's cluster. Yeah, and we have the southern ring here. Yes, we do. And then we have a few. Then we've got M8 over here. Let me go move the dome so that we can look at M8. All right. Because it's 23 degrees above the horizon. So I think that's actually not terribly bad. It's it's just approaching the highest point that it can be. It's actually just around the highest point it can be in our sky. So why don't we go check it out? Shall we?
Okey-dokey. I'll try to keep people entertained or at least occupied till you get back.
Oh, I'm sure that you will have no problem with that because you are okay, Daryl. All right, guys, I'll be right back. I'm gonna go move the dome. I'll be right back.
Where Mark is moving to is the M8 Lagoon Nebula. It's just off the tip of the spout of the teapot in Sagittarius, and it's not far in the sky from the center of the Milky Way. It's not really anywhere close to the center of the galaxy, but it's a short hop, skip, and jump from where the Sagittarius A star is in the sky, which is the big black hole at the center of the Milky Way galaxy, just a little bit above it. And M20 Trifid cluster is another pretty nebula, which sits just above M8. I'm sure we will look at it also. Then there's a whole chain of M objects and nebulas and star clouds following the Milky Way up from there, up toward the northeast. And I bet we looked at a few of them. And maybe Mark will show us when he comes back. We can get a planetarium view of the teapot itself, which is always neat to see to me. When you see the teapot in the sky, that's what the ancients saw as Sagittarius the archer, a centaur, a half man, half horse, shooting a bow and arrow. What we see is an asterism, an unofficial star pattern. It is shaped like a teapot with a spout to the right, handle to the left. It's funny how culture dictates, what patterns we draw in the sky. But then the steam from the teapot is the Milky Way coming up right out of the spout of the teapot. And as summer progresses, you will see the teapot, as it moves from east to west in the western half of the sky, it will start tipping over down and to the right. And people say that is when the teapot is pouring the tea. It's tipped over like you're pouring the tea, and the steam, which is the Milky Way, is coming up out of the spout then. It's Big Mark. Welcome back.
Hey. What'd I miss?
Nothing, just me blathering.
Well, you're a very intelligent blatherer.
Oh, I just talked about M8 and M20 and the whole chain of nebulas and clusters going up the Milky Way, and I talked about the teapot some, and
That's good.
how the Milky Way makes the steam coming out of the spout of the teapot.
Yep, exactly so. All right, I've gone red again, and now what I'm going to do is I'm going to take us over to the lagoon. So we're going to go back there, and you'll watch as we zip away from where we were. It's going to be so nice to see the lagoon tonight. Haven't seen it in a year.
Really? It's been so long?
Oh, yeah. And now we're going to do that again here. All right.
A lot of people might say that M8, Lagoon Nebula, is second best thing in the sky to look at after the Orion Nebula in the wintertime.
That's right. And if you're far enough south, then this nebula that we're going to be seeing, we're just aligning on a star, and you'll see that star disappear like you just did. And then Messier 8 comes into view right there. Now, but one of the things is if you're far enough south, Messier 8 is just one of many nebulae and not the best one for you. The best one is probably, I'd say the Tarantula Nebula, wouldn't you say?
That's what I've heard.
And
they say if the Tarantula Nebula was at the same distance as the Orion Nebula, it would fill half our sky.
Amazing.
That would be something to see.
Yeah, we've taken pictures. We've taken pictures of the beautiful hydrogen regions inside of Messier 33, which is a spiral galaxy in Triangulum, and these beautiful hydrogen regions there are so extensive that we can see them from over 2 million light years away, and that's just beautiful, stunning, you know.
From 2 million light years away, would you be talking about 2 million light years away, M31 comes to mind, but M33 also.
Yeah, I was saying M33's H2 regions, the hydrogen.
Yeah, because I know they're more prominent than M31.
Yes.
The H2 regions, that is.
Yes, that's right.
It's got that one great big one up on one corner.
That's right. And we love looking at that one.
Oh, yeah.
Okay. So I'm centering this in here now, and what I'm going to do is I'll do 15 seconds, and this is at 50 ISO, which is the sensitivity, but as I go higher, you'll start to see there's some red showing up in here. And if I actually go into a video mode here and pump up the ISO even higher, now you can start to see this nebula showing up with the camera's eyes. This is what your eyes don't see unless you look through a telescope. I mean, your eyes can see a fuzzy thing in the sky there, but look at how it looks when you look at it this way. Now let's go out of that mode and just take photos now, and we're going to drop down our ISO to something reasonable. Let's say 15 seconds at 3200. I should have been able to capture a guide star by now, so let's go. And we're off and running. We'll see what happens. And our sky looks nice. That's good. We're actually looking down here into the Milky Way. And let's go see what we got. Okay, this is a greatly magnified view, and what I will do is back out of it and to show you what we actually captured. And there you see the beginnings of the Lagoon Nebula. Really looks pretty. The Lagoon, yeah, and you'll notice this area right over here. Okay, this area is very special, and I'll tell you why. Because you can't really tell. Yeah, and we're gonna do some more shots of this momentarily, but this little hourglass shape right here, that's actually a very, very important spot in the nebula, because there is an O-type star that's illuminating this nebula. O-type stars have a lot of high radiation, very, very high energy, very hot. They ionize a lot of the hydrogen gas, giving rise to this reddish glow that you're seeing here. And the O star here that's illuminating this nebula is solely responsible for much of the illumination in this area. And when you see a star of that brightness, it's actually able to illuminate and bathe the area, the gas, in for light years around it, with ionizing radiation to cause these electrons to bounce off the atom, and it actually can be responsible for many light years worth of glow, like we see here. Really just fascinating, So what I'm going to do now is take us back to our view here, and I'm going to up our ISO a little bit. I'm going to go up by 2 stops, taking us up to 5,000, and I'm going to go up to 25 seconds. So this is 4 stops, effectively. And let's see the difference between 4 stops. And this is just the Lagoon Nebula Messier 8. On ultra clear nights, there's a lot of moisture in the atmosphere right now. We just had an awful lot of moisture in the atmosphere, a lot of rain and so forth. So when you look down toward the horizon, you actually can see that there's a lot of water vapor in the air. So we're not going to have the clearest view tonight, but we do have that, however, which is a guiding error. I'm going to fix that in a second. Let me go in here. Do that right now. So jump into the computer.
Mark, the O star you mentioned, is that the one visible in the image just to the right of the hourglass, or is the O star actually down in the center of the hourglass?
I think it's to the right, but in fact, let me fix this here. We can figure that out.
Sure.
I believe it's the one that we can see. All right, let me first let me go back to our other view here.
Could you excuse me for a moment, please?
Sure thing. All right, folks, I'm just going to go and try to fix that problem. All right, so we're going to go here, and we're going to go and go down, and 1, and say this is the 05 is a parameter that I enter to tune the auto guider, and I go down 1 more and enter, and now this is a parameter for that error that we just saw where the thing was jumped way up and vertically. Okay, so that's there. Okay, now let's see how that works. Do the same thing again, 25 seconds, and we should see a very different image. And again, by the 20th of July, the comet will be higher in the sky and we'll be able to see it. I was hoping to see it tonight. It was there very briefly, and by the time we were ready to stream, before it was even dark enough, unfortunately, the comet had gone behind the trees. Okay, that's better. Yeah. And I'm noticing we had a cloud come through there. Let's go look at the all sky and see what came through. We're looking down here, so we must have had a cloud come through during the exposure. And the clouds will always look like this sort of orangey looking. That's the reflection off of some sodium vapor lamps that are in a distant town somewhere. and we're of course seeing it. So not terribly exciting, but at least we know that we're on the right track. All right, good. So let's go back and take another image. All right. So I just want to say thank you to you guys for being here. I'm really happy to have you here exploring all this with us. I'm going to go up to 30 seconds here and go up to 2 more stops. And by the way, we're doing this in white light. We're not using any filters at the moment. That'll change, so I'll change it. That's right, TP Seeker. P&K are great. They're good friends and good people. In fact, because of them, I'm streaming. They convinced me to do it along with Bill Skywatcher. So that's the only reason that this is happening now, is because of them. But once I started doing it, it was really amazing. I could actually do astronomy every day. And it's really, really cool. Wow, look at that. So this is a white light shot. So we're not actually looking at this in light that is actually the best for what we're doing. I'm going to go now and take and get a filter activated. All right, and I'll show you that right now, actually. So we'll go back to our main screen here, bring up our system. For those that have been here before, you know what this is. For those that haven't, you learning now. This over here is the telescope control cluster. All right, this controls where the telescope is pointing. These are coordinates. I can look for objects in different ways here. This is the computer access. I get into the computer of the telescope here and do commands that I memorize and just enter input codes. Down here is a filter wheel, and right now we're on filter wheel 5. See, it says position 5. Now, if you watch the screen, this is a live view. When I go to filter wheel 1, you'll see that something will pass in front of what looks like the image, and that's the middle of the filter wheel structure. So here we go. There it goes, and now filter wheel 1 is in place. That's a narrowband filter. So we look specifically at certain wavelengths coming from such things as nebulae. A slightly wider narrowband filter is this next one. Okay, and you'll see we see more stars and just a hint of nebula. So it says, you'll say, well, hey, that's not showing us too much, but in fact it does. It shows us more than just white light. Filter wheel 3 is a spectral one, and we see the spectra of the stars. And if we analyze each of these spectra, we can actually see that there'll be different dark lines in the spectra that tell us what are in the stars. Now we have a system now that I have received from France. It's a spectrometer that will be implemented for the Arizona telescope, and it will allow us to actually look at the spectra not of just stars and so forth, but nebulae as well, and comets, and we'll be able to look at the spectra of everything we see based on the exposures we can take of them. So that's a really, really good system that we're expecting to implement here. And it's tricky. There's a lot to do, but I can't wait, because that will bring us into the realm of doing some real astronomy beyond just what we're doing here. Wheel 4 is actually a black wheel, and that gives us a dark view if we want a dark view, and we need it sometimes to calibrate our system. And then 5 we're familiar with. Okay, this is the white light view. But we're going to go back to filter wheel 2, which is the wider narrowband filter. So it's looking at very specific wavelengths, but a little bit wider on each side of each filter to give us a little bit more of a view. Hey, Kyle Lynch is here. Welcome. Good to see you. And Big Trips. Big Trips keeping it real, man. How you doing? Thank you for joining us. We're taking a picture of the Lagoon Nebula, and I'm going to go up to, let's see, take it up to 12,800 ISO for 30 seconds. Here we go. Oh boy, you're going to win now. So this, Daryl, is the earlier image we took when you decided to You went away for a few minutes.
Uh-huh.
This was a 30-second white light shot. These are all white light shots. The next shot that's coming in will be the filtered shot with the wider narrowband filter. We'll see. And this is really, really pretty as well. Again, we're still looking through a lot of moisture and water vapor in the sky. But it's still a beautiful nebula. Now, look at the difference, though. Okay, so
Very nice.
if you folks remember, okay, this is the white light shot that we saw earlier. Okay, now you add a proper filter. Look at the result. Wow. Now you see dark clouds of gas and dust, right, inside and hiding in this nebula. This is stuff you don't see here, do you? Right, because the white light doesn't show it to you. You've got to actually selectively pull in those colors that have specific wavelengths, and that's what the filters do. And there you go. And that is a nebula. Okay, now that's cool. It looks really pretty. That's my first view of the Lagoon Nebula this season.
And since you got all the new filters, right?
Yeah.
Very
Yep.
nice.
Yeah. Wow. Yes, indeed. I feel like I'm in the nebula over here. It's like, look at me. I'm in the nebula. This is beautiful here. Now that star right there you're talking about, Daryl, that one there, that's the O star that's illuminating this nebula.
Yes.
This entire area is being illuminated by that one star. And if you think that's impossible or you can't see how that can happen, let me remind you of Sigma Orionis, which is that little multi-star system that's near the Horsehead Nebula, south of Zeta Orionis. None of that means a lot to some of you, but that is a star that's responsible for illuminating several light years of hydrogen gas and causing it to glow. And against the backdrop of that glowing hydrogen, we see this dark nebula known as the Horsehead Nebula, which is where that comes from. And it's one of probably Daryl's favorite stars, I believe, if I don't
miss
my guess. Yeah.
Absolutely.
Mm-hmm. Yep. So this gives us an idea of what's going on. And of course, then we have this cluster right here. This cluster inside the nebula is, of course, very important as well, because what's that telling us is this cluster right here is, born of this stellar nursery. Now, large gas clouds like this tend to be nurseries, that is, where stars are born. And this cluster is no different. And this nebula is no different as a stellar nursery. It actually has lots of stars that have been born in this nebula. And then they interact gravitationally, moving around each other, orbiting each other. And that whole process is very dynamic. And over time, some of these stars might get whoop and ejected right out in all these different directions, possibly. And the cluster will then break apart and dissipate. And some of the gas will stay here, and some of the bright stars, like this star over here, will continue to illuminate the nebula. But that star will eventually go supernova in just a few million years from now. So everything you're seeing in the universe is transient. Okay? They're transient. It'll be gone within a certain amount of time. And the reason it has to do with the evolution of objects in the universe and the way large stars, for instance, work in the universe. These big O stars, like the one that's powering this nebula right here, these big O stars are absolutely they're massive giants, okay, of output, but they burn through their hydrogen very quickly. And then what happens is they burn other materials in their outer shell. They'll contract a little bit, and then they'll bring more stuff into the center, and where the temperature gets hotter, and then they can fuse higher and higher elements in the periodic table. The higher you go in the periodic table, the harder it is for a star to make those things. And you can only go to number 26, which is iron. And we have like 100 and some odd elements in the periodic table, don't we? So where do all those come from? There's a variety of processes which cause the creation of those elements One of them is a very slow process, and it's called thus the S process, or a neutron capture. And if you look at the periodic table, let's say hydrogen has 1 proton and 1 electron. Simplest atom, right? Now, if you add another proton to a hydrogen atom, what do you get? Helium. That's a helium atom, okay? 2 protons, and then an electron will get captured to make another helium atom. Well, what if you take a neutron and add it to a hydrogen atom? So you have a neutron and a proton in the nucleus. Those are always in the nucleus, all right? A neutron and a proton in the nucleus of a hydrogen atom. And then you have an electron orbiting those, right?
Deuterium?
Huh?
Deuterium?
Yeah, that's right. That's deuterium. That's right. It's called an isotope of hydrogen. Now, all isotope it means is that it's a variation of the same element, okay? And a deuterium atom, or a hydrogen atom that has an additional neutron in the nucleus, can go through a process where that neutron gets transformed into a proton. And that neutron becomes a proton, and now there's 2 protons in the core of this atom, and thus it's now a helium atom missing an electron. And so it'll gain an electron over time because there's free electrons in some of this soup in which these things are created, and thus we have helium atoms. Now just ratchet that up to heavier elements in a star's atmosphere, and you can see how you can slowly make other elements by adding neutrons into the nuclei of some of these other atoms, and then those neutrons get transformed into protons. Boom, you got a new element, a heavier element. Okay, that said, and I'm purposely not going down the path of how neutrons are made into protons. That has to do with learning about up and down quarks and all things like that. But suffice it to say that if you really want to know about that, then you can take the astronomy course I'll be teaching before long, actually. And we can do that and talk all about this in such cool ways with cool labs. So anyway, but keep in mind that when we talk about these hydrogen atoms and other elements, they will gain and they will generate other types of elements. Stars like our sun can make other elements in its atmosphere through this special neutron alteration process, as we'll call it. Okay, and big heavy stars like this guy right here, these guys don't do that. In fact, that's hot. These guys you don't want to mess with. Okay, they're very hot, and when they run out of their fuels, then it's like somebody running down a track at high speed and suddenly their feet fall off. The only way to go is down. You're going to crash, and that's what happens to these stars. They're going so furiously through their fuel that there's almost no time for them to recover when they run out of their predominantly, majority of the fuel. And so when they burn through their hydrogen, they might start fusing helium into carbon, then nitrogen, oxygen, fluorine, other materials, and they can get all the way to iron. But then they can't go past iron. They can't fuse any other atoms into anything beyond iron, because for that process to occur quickly requires more energy than the star gets back. So it's an energy sucking in, it's an energy using reaction, not one that generates energy like all the others. So the process ends there, and when you can't generate any more energy and you've used up all the nuclear fuels, the energy of the star has been balancing the gravity, trying to crush it. Its own gravity trying to pull it in versus the radiative energy pushing outward from the core of the star. And so when the radiation energy outward stops, this collapse goes shboom, and the star collapses. And all of that mass of the star from all around the star is colliding in this one little tiny area in the middle, the nucleus, where the iron is located, the iron that could no longer be fused into anything else. And that collision causes new elements beyond iron to be created. And it's a one-time process because the star is in the process of obliterating itself right at that point. And this is, of course, the what we call the core collapse supernova, or the Type 2 supernova. And the Type 2 supernovae, these core collapse supernovae, will cause a star to be utterly and totally destroyed. They release an immense amount of energy. They create lots of new elements in the periodic table, and then they proceed to blow them out into space all around the remnant of the star. Well, guess what? That's what's going to happen to that star right there. That little guy is going to eventually blow up, and it's going to liberally spread most of its content to the rest of the universe. Now, why would I say most? Because there'll be something left over in the core of this explosion event. And that could be a couple of things. And I'll give Daryl the first guess. I'm sure he knows, actually. What's one of them, Daryl? You're still there, right? He's on mute.
Sorry, I'm on mute. A black hole or a neutron star.
That's correct. You either get a neutron star or a black hole. A neutron star, if the star is not very high mass relative to the sun. Now, what's that mean? A star that's 8 to 10 masses of the sun could create a neutron star. Under certain circumstances, the higher mass stars can create black holes as well. And so there'll be something left over. But the neutron star was a real odd thing, which we'll talk about another time. But that star right there is going to go. And when it does, I'd love to see it. Just like we know Betelgeuse is going to go, if it hasn't already. Betelgeuse is the upper left star in the constellation of Orion. And it's about 700 light years away, and it's going to go supernova. It's in the last stages of its life. They think maybe about 10,000 years. On the scale of the universe, that's a blink of an eye. A blink of an eye. Let's, I'm going to go back, actually, and take some more shots here while we got this. We also have to do something else. We have to, because we're using another filter now, we need to refocus, which I didn't do before. And I really think we need to. So I'm gonna get us to, I'm gonna get this thing to refocus. All right. So let's do that.
Genghis, a pulsar is a special case of a neutron star.
That's correct.
It's rotating rapidly, and it's emitting radiation, radio waves, I guess. And if they tend to sweep us, we see it as a pulsar.
Right, they're like lighthouse beacons.
Yeah.
Stellar lighthouses. And as it turns out, those beacons are literally hot spots on the surface of the pulsar. That is the remaining core element of this neutron star left over from the supernova. And that core can spin sometimes very quickly. Like we know about the Crab Nebula in the constellation of Taurus. The Crab Nebula has at its core, that's a supernova remnant, at its core is what's called the Crab Pulsar, one of the first ones that we ever found. And it spins 30 times a second. Now, what does that mean? It means that something the size of Manhattan Island is spinning around as a sphere 30 times a second. Now, anything moving that fast would rip itself apart because there's no force that it could hold itself together that would with that kind of size and that kind of rotation rate. But the neutron stars are so massive and they're so compact that they hold together at those rapid rotation rates. And guess what? That's not even the biggest one. I should say the fastest rotator. The fastest rotating neutron star is just above 700 rotations per second. Imagine that. Again, something the size of Manhattan Island. What was that, 25 miles, 30 miles long? Okay, maybe I don't remember how long a Manhattan is. But as a sphere, a solid sphere of highly dense material. And it's rotating so rapidly that it's actually rotating over 700 times in a second. Holy cow, that's got to be powerful gravity to hold that together. In fact, that's such a powerful gravitational field, it corresponds to this highly compressed mass Well, that mass is compressed so much that we're looking at easily just over 1 billion tons in a teaspoon. 1 billion tons. It defies normal logic and understanding. That's 1 billion tons as measured on Earth. Yeah. And yes, Tara, that's incredibly fast. Very, very fast. Yeah. So, I'm taking a 1 minute shot here of the Lagoon Nebula now. And while I'm waiting, I'll just go out and check the telescope. And you might see when you look at the telescope, you actually see here there's this arm that's coming down here. This arm right next to the telescope. Okay, let me get back in here for a second. Oh, wow. Jeez. Never mind. Let me just move this out of the way. I'll tell you about that in a minute. Look at that. That's beautiful, huh?
It is.
Yeah, this is a 1 minute exposure of the Lagoon Nebula. Jeez, that's beautiful. Oh, I missed you, Lagoon. And let's take a look. This is neat here. I'll just show you what's going on here. Okay, when we look in the middle here. Okay, that's a little too much. Here we go. All right. So we look in the middle here, and now, okay, you see this dark area? This is dark clouds of gas and actually dust. It's dark dust inside this nebula, which actually is being shaped by the solar winds, the stellar winds of the hot star that's actually illuminating this nebula over here. Okay, and it's shaping this dust, and that dust is actually blocking the brightness of the nebula behind it. Okay, so we're seeing in front, this dust is superimposed over the nebula behind here. So that's really what we're watching here. And then we've got this bright area here that's illuminated by that star as well. And there's dark lanes, dark dust all throughout this nebula that you can see everywhere with all these beautiful little intricate areas. Look at this little intricate area right here. Isn't that beautiful? I mean, this is just so cool, and that's neat. And this is what we see in these stellar nurseries. Now, you can see how that cluster, okay, over here, you can see how that cluster is actually involved fully in this nebulous detail here. You can see that there's a lot of it there. You can see that there's even more like up here on the corner here. You can see a lot more up here as well. So we've got nebulous detail everywhere we look. There's little tiny areas here, really cool stuff. We have all this lane of material all throughout here, which is all dark dust again, and that the nebula itself is mixed and interspersed through all of this dark dust, and so we get this very complex view of the nebula from here. Really, really beautiful. And with this particular filter, it's so much better than seeing it like this, which is the best we could see it. This is actually an approximate view through a relatively modest telescope with an eyepiece. You might see it around like this. Okay, maybe a little less detail in this area, but you'll see this nebula, but you won't see any of this. You might, but maybe most likely not. But you certainly need a telescope with a good filter to see this. But this is really pretty. Look at that. And sometimes when you frame it like this, it looks even better. Isn't that pretty, Daryl?
It sure is.
Yes, it is. Yeah.
I could think of only about one other thing you could look at that might come close to that.
Tonight?
Yeah.
Besides the Trifid Nebula?
Well, no, I was thinking the
Omega?
Trifid M20.
Yeah. Yep. We can look at the Trifid. I was going to go to that next, but I thought we'd also be able to check out the Omega Nebula as well.
Sure.
Now, not all stellar nurseries are still acting as nurseries. Some of them are done with star formation, and what's left is this glowing gas that's left over by the stars illuminating it that were created there. And in this particular case, this is an active stellar nursery, the Lagoon. The Trifid Nebula we're about to go look at, that's an active stellar nursery. And when we get to the Omega Nebula, that is not an active stellar nursery anymore. It's not undergoing any nursery activity, shall we say. It's sort of dead in that regard. But we're going to leave the Lagoon behind for a few minutes. I'm just going to actually, I want to actually take this so we can, I want to try and move this actually. Move this guy over there. Alright, so here we go. We're going to now move over to the Trifid Nebula. Here we go. You'll watch the stars shoot away, and they're gone. The telescope works by going to a nearby star that it knows, and it will take that star, center it up in what it thinks is the center, which is fine. And once it has that star in the center, which is this star right here that it's using, all right, which is Alnasi, is that Alnasi?
Al-Nasal?
Alnasil? Is it Alnasil? Yeah, okay.
Yeah.
Yeah.
That's
then
the tip of the spout of the teapot.
yeah. So once that's centered, which is right there, and it's happy, boom, it goes away and takes us all the way up to the Trifid Nebula. And we'll see the telescopes coming in here. Yeah. And then I do a finder shot just to see where it is in the view. It's right there, I can see. The giveaway is you see two little stars there. That's the thing that kind of helps you figure that out. But I'll do a finder shot. And what's neat is this particular shot's going to show you a very cool image. This will be 15 seconds at 12,800. I'm just waiting for my finder, my guider to work. Let's go see what the telescope is seeing. The all-sky camera. Yep, we're doing good out there with the all-sky. Okay. There's Vega right there. There's Deneb and Cygnus. There's Altair. Yep. And so we're actually looking at a beautiful all sky. This is the Milky Way here. You can see the Milky Way. Now in Arizona, that's going to be dominating the view. It's going to be stunning, and it dominates the view for sure. So let's go and do this. Let's drag this little double guy right here. We're going to drag him over a little more. We're going to head to the west a little. And we'll stop there. That's good. And now we should have... this should be a beautiful view of the Trifid Nebula. But let's do a 15 seconds at 12,800 just to see. 12,800 ISO, that's the sensitivity of the camera. Okay, this is the camera control over here. Telescope control is this section, as I told you. This is operations, that's me, hello. And there's the telescope right there, that's the telescope view. And this is the camera control. And this is the live view. And that said, boom, there's our Trifid Nebula. Look at that. It is really, really pretty. That's pretty good. You know, and I told you about that, what looked like a little double star. That's these guys right here. That's these two right here. Isn't that pretty? And once again, like the Lagoon, you see this dark stuff here? These are called dark lanes, but this is actually areas of dark dust that is obscuring the nebula behind it. You'll also notice there's a blue thing up here. This blue thing up here is actually another nebula. All right, and it's a different type of nebula that's based on something called scattering. We talked about the blue sky before. Well, the same type of scattering, similar type of scattering, causes the blue light we see from this nebula up here, and it's called a reflection nebula. So it's not exactly a reflection, but it is a scattering nebula for sure. And then this is a hydrogen gas nebula, that where the hydrogen has been ionized, and that ionization process, when the electron gets driven off the atom, it absorbs a lot of energy from the central stars here that are really heating it up, and it absorbs energy, it bounces off the atom, and then it collides with other electrons out there, and then finally loses enough energy to fall back into the hydrogen atom. And when it does, it lets go of one more bit of energy as it falls to a particular energy state in the atom, because there's discrete energy levels, and we call them N numbers, like N is in November, N1, N2, N3, etc. And when the electrons fall to one particular state called N equals 2, all right, as in numeral 2, that gives off a particular color of light. When they enter the atom again, it's called recombination. As they enter the atom, they're releasing energy to get back into the atom, all right, and reconnect with the atom, basically. And that release of energy is in the form of light. Guess what the color of that light is? In hydrogen's case, it's this red color here, known as hydrogen alpha. And that's a 650 nanometer, roughly, wavelength. So it's in the red end of the spectrum. So let's go and take another shot of this, but let's go up to a minute and see what we get. We're going to go right past 30 seconds, and we'll go right to a minute. And we'll go down one level here. We'll go to 10,000 ISO. All right, so now we'll see the Trifid Nebula in a 1 minute exposure. Now the Trifid is actually a little higher up, all right, and so when we look at the Trifid Nebula, it's above the Lagoon Nebula. We were just here, and now we're up here. And then shortly, we're going to go up here, all right, and we're going to find our way up and away to this nebula right up here, which is probably going to look stunning tonight. It's called the Eagle. And then we'll probably go to the Omega Nebula first, because it's along the way, Now, when you see in here, you'll notice that there's all kinds of stuff. This cloud, this is the Sagittarius star cloud here. This is where the center of our galaxy lies, in that direction. So it tends to be very busy in here. Lots of stars. We're looking through the thick of the disk of the galaxy. It's really gorgeous. All right, let's go see what we got in the 1 minute shot. Wow, look at that, huh? So there's our 1 minute shot of the beautiful Messier 20, or the Trifid Nebula. And again, we're seeing these beautiful, beautiful dark lanes in here. Very, very complex dark lanes. You see them? And I'll tell you one thing I really like too. There's something I want to show you. This right here. Do you see that little that little loop right there? That little bright area? I really like that right there. That's pretty cool looking, because you can actually see it almost looks three-dimensional, in that little area. And I like looking at it every year and during the summer, because I like to see if I can see any changes. Now, if there's stars that are illuminating it, if there's stars that are causing it to glow, if the stars change a little bit, then that'll look differently. And that could be in as little as a few weeks. So that's something that's really a lot of fun to do, is to look for changes in brightness of things. And we know one nebula that actually does do that, and we see it a lot. Now it's in Messier, which is to the left of Orion when we're looking at it, and it's called, Daryl?
I Times Variable Nebula?
Hubble's Variable Nebula.
Excuse me, Hubble.
Yep. Yep. And it's a beautiful nebula. And many times...
we see changes in it, like on the time scale of days to weeks.
We do. We do, actually. We have. It's pretty cool. So here's the Trifid Nebula. Again, this is another stellar nursery, and an active stellar nursery. And it's really, again, one of the beautiful summer Milky Way delights. It sort of sounds like an ice cream, summer Milky Way delight, or a candy bar. But it's really pretty. But now I want to take us up to the Eagle Nebula. I'm sorry, the Omega Nebula. The Omega Nebula, unlike the last two nebula we just looked at here, the Omega Nebula that you're about to see is an area where they think star formation has pretty much come to an end. And that may be true. But there go our stars. Our telescope is now moving. And we're heading up in elevation. We're going to another star here. Which star are we using now as a guide star? We're up here. Good. We're using a star called Psi Ophiuchus. Or is that Psi Ophiuchi? Or V? It looks like V Ophiuchi. Nu Ophiuchi? It could be. Yeah, Nu Ophiuchi. That's Greek letters. All right. But the Omega Nebula, where we're going to be here shortly, is a really beautiful location. All right. And the reason is because the Omega Nebula is that nebula that I said has ceased stellar formation. And so we'll let it calm down here for a minute, and then we're going to take a shot just to get it centered up. We'll do, again, 15 seconds at 10,000. I'm going to do this now because that way I can change it in a couple seconds. But keep in mind, everything in the universe changes moment to moment. Oh, look at that. That's a 15-second shot. Wow. Nice.
That's the one I always think of as the upside-down duck.
The upside-down duck?
Mm-hmm.
Oh.
Sort of like a duck decoy lying on its back.
Like that?
Yeah.
Oh. So the head is up here.
Yep.
Here's the body. Okay. The upside-down duck. I never thought about that.
Sometimes they call that the checkmark nebula too, if I remember right.
Yeah, I think you're right. Huh. Yeah, but this nebula, and again, this is only 15-second exposure. It's kind of crazy, isn't it? This nebula actually is no longer sponsoring any stellar formation. So it's lost all its sponsors. It's lost all those sports contracts. Hey, it's sort of a dead-endula. Okay? Sort of a conglomeration of dead-end nebula. It's a dead-endula. But that's okay. I mean, it's really a very pretty location nonetheless, and serves us well in terms of trying to find really interesting stuff. This is 15 seconds at 10,000. Let's see what 1 minute at 10,000 looks like with this guy. I bet you it's gonna look really pretty.
I bet you're right.
I bet I am. Yeah. Yes, Tara, this is quite an interesting nebula. You'll notice that it doesn't seem to have any very bright source stars. And Genghis says, yeah, celestial smoke. In a sense, right? Because it's being, the nebula is being caused to glow by the light of a number of the stars that had once been created in it. But this is a dark nebula here. And you can't see the stars that are inside this nebula. But there's going to be some in there that are going to be causing the nebula to glow as well. All right, so that's pretty interesting how that works out. Now, when we see the 1 minute shot, and provided the guider did a good job, we'll be able to actually see a little bit. Oh, that's better. That's really nice. Sorry, I got a creature flying around here. My screens are the only thing that are on, so I got a fly flying around in here. Look at that. Holy cow, that's really pretty. I wonder if we can do any work on this one here. Let's just take our color correction here and try to see if we can shift it toward actual colors. We want to actually go in this direction, but that makes it too orange. Okay. Like this, maybe like this. Well, I mean, that kind of shows you a little bit more of the detail, but I prefer the softer view initially. So in other words, like this, which is sort of like the basic. That's beautiful though. Hi Omega, haven't seen you in a while. You know. And then right on its heels, we have another one. And it's going to be the Eagle Nebula, but there's a lot of other objects out here to see, Daryl. But I guess we should just go to the we should probably just go to the Eagle Nebula, huh?
Yeah, Eagle's popular.
Yeah, sure is. Okay, here we go. Off we go into the Eagle Nebula. Wind our way into the sky. And we're going to go to VO Fuchsia again. And from there, it knows exactly where to go to get to the Eagle. The Eagle is still an active stellar nursery. So when we go to the Eagle, you'll see through the view here on the left, you're going to actually see up here, you're going to see a cluster of stars, right? Because that's what is in the center of the Eagle Nebula, is a cluster, a young cluster of hot stars, right? So you'll see that coming in any moment now, and there they are. These are the young stars in the middle of the Eagle Nebula. And those guys are responsible for illuminating the Eagle Nebula. Hi guys, I haven't seen you for a while. So let's just give that a shot, and we'll do our finder shot. This time I'll do like 25 seconds at 10,000 just to see what we got. A toxic wolf. What do you mean you were bamboozled? Yeah, the comment wasn't out long enough, and I was telling people that all along tonight. No bamboozlement. You know, we're gonna see it on around the 20th or so. It's gonna be high enough into the sky where we're gonna be able to see it. So I couldn't. Unfortunately, we couldn't see it. So there was no bamboozling going on here. I'm not like that. Ask anyone. Okay, so let's do a 25-second shot now of the Eagle. And here we saw the Omega Nebula. And here we had the Trifid Nebula. And then here we had the Lagoon Nebula. And then beyond our last Omega Nebula, we should now see the Eagle Nebula showing up. Look at that. Wow. It almost looks like this is a stain, doesn't it? It almost looks like that's a stain. That's actually the pillars of creation right here that we're seeing. And when we process this, it looks really, really pretty. And this is only a 25-second shot. Why don't we do 1 minute? All right, we'll do 1 minute shot. And at 1 minute, I'm pretty sure that it's gonna have quite a different effect on you. All right, here we go. Now our telescope can take images, you know, in the range of anywhere from just a fraction of a second all the way to many, many minutes up to hours. But I'm not going to make people sit here for hours to see a nebula show up. You know, that's not going to be the case. I'm going to do my best to try and show you something in a reasonable amount of time. And for me, reasonable is 1 minute exposure or less. So that's SkyTour LiveStream, 1 minute exposures or less. So
When you said pillars of creation, you're referring, of course, to the famous Hubble image.
that's correct. Yep.
Which focused on that central dark portion there.
Yep, that's right. And which you'll see much clearer here in a moment. And there we go. Look at that. Wow. I missed you guys. Yeah, these are the pillars right here. And there's noise from the camera in here. Again, but that's the stuff that I process out. As a matter of fact, if I don't miss my guess, I think that right there, our welcome screen for tonight, this was one shot like that I modified to actually I processed to actually show much better. And this shot illustrates that. Okay, we have these pillars of creation right there in the middle. All right, but that's the process view, and this is the actual live view right here. Okay, not live view. This is the actual shot of what it looks like out of the raw camera shot. Pretty cool, huh?
I have always wondered, they call it the eagle.
Yeah.
Can you bring that back up? Or are you taking another image?
Yeah, just a second. They call it the eagle.
The eagle's wing is to the left, its head is to the right, and like its claw, its foot is to the lower right. That's the way I always saw it at any rate.
Yeah. Honestly, I never saw an eagle in you know, looking at it. I have no idea.
That's what I always saw. See, the head there is to the upper right, and that's his foot down below the head. And then his body to the lower left, and the wing to the upper left. At least that's how I always saw it.
Okay. I don't see it. But that's alright. I didn't know if the eagle was supposed to be just the eagle's head. Like this is his beak, and this is his lower beak, and this is the eye. You know, or what, you know. Again, it's almost just a it's a strange it's a strange way of visualizing things, you know, to try and put a picture to them. I always thought that looking at stars in the sky and trying to connect dots to make pictures just always seemed so silly to me. But I understand that in early days, when you had nothing but beautiful starry skies, you could lay out under them all day long, all night long, and just imagine all kinds of things going on up there. And I thought that's kind of a pretty cool revelation, you know. And so I imagine that would work, and that would make you have a very good grasp of the night sky. You know? So, wow, this is it's really a pretty night sky there. And a lot of this noise is due to the water vapor in the air. Now, I'm going to try something, though. I'm going to try another exposure. We're doing a bulb shot here for 1 minute. I'm going to try going 2 full minutes just on this one, just to see.
Well, you step down your ISO.
I am. I'm gonna step the ISO down to maybe 6400, and we'll see what we get. Telescope's guiding pretty well, so I want to see what it does. Getting a set very good. The pareidolia allows you to see anything you'd like to see. You try to make a known pattern out of an unknown pattern. And it's something humans have done for a long time. In fact, we evolved to doing it. I think we evolved into doing this because we were always looking in the dark for threats. So we'd say, what is that shape over there? Is that a panther's head or a lion's head coming at me? Is that a gorilla trying to come in to attack me? And we would try to build imagery in our heads of what we're seeing in the dark. And that may be the origins of pareidolia evolutionarily.
Yep.
But it's a really, it's useful. It's helped us in our evolution. Well, thank you, Tara. I'm glad you could wait for 2 minutes. I keep talking anyway, And Kyle, I'm not sure what the dew point is tonight, but I do have a anti-dew system on the telescope, so I can go out there, and even inside the dome, the mount and everything is soaked, but the telescope is clear of dew because I have the heating system that is isolated only to the telescope. As you know, heat in a dome is not a good thing because it'll rise and cause turbulence in the atmosphere of the dome. And turbulence causes unsteady images. Unsteady images look terrible. But that's something that we don't have to worry about, So there's our. That sounds like an arrow, Daryl. It's like an arrow, like you're shooting arrows.
I'm sorry.
That noise sounds like you're shooting arrows into something. It's like I don't know what that noise was, but it was actually kind of cool. It sounded like you were shooting arrows.
I'm sorry.
No.
I'm not sure. I bumped my microphone at one point.
Yeah, maybe that's what it is, but it was fine. I thought it was a cool sound.
I make a lot of noise. I apologize.
No, that's okay. It was older. It's I'm like a sound engineer at heart. Trying to identify sounds and use them for things. There's a Trifid. There's a Lagoon we looked at. Yeah, it's beautiful. And in visual light, it's really that's the Lagoon. It looks rather unassuming, doesn't it? But you add the right filter. What a difference. And now we're waiting on a 2-minute shot of our Eagle Nebula. Gosh, I can't wait to see it. What's it going to look like? Apparently, we saw it already. I must have got it already. This must be it?
Yeah.
Wow. Yeah, well, that's interesting. It's this one's noisier because it's much noisier. Now, if I go to this next one, okay, it has less noise. Things are a little more visible. Then this one is dimmer. Yeah, we basically effectively went up one stop, dropped a little of the noise. But man, it came out really nice. It's like I'd really love to do like a 10-minute shot of this, but that was, yeah, you do like 30 10-minute shots. So for 300 minutes, you're gonna sit here just doing this. Then you stack them all and get an image at the end. I think that'd be pretty cool. I'm not gonna do it tonight, guys. No, don't worry. As I said, 1 minute or less on SkyTour LiveStream, unless we actually do a special shot like this. So let's see. Where would you like to go now, Daryl? Do you have any ideas where you'd like to go? We checked out all these nebulae.
Golly. It's kind of an embarrassment of riches in that area.
I know.
Would you have to move the dome to get the wild duck cluster?
M11? I don't think so. I think that's up here. Kind of near where we are now.
Yeah, it's in constellation Scutum, I believe.
It's right here. Yeah, let's just see what happens. A wild duck is an interesting place, so we're going to leave the eagle behind. You'll watch the stars vanish here. And we're going to go to another location. Here comes our telescope. You see it moving. Which star is it going to be? It's going to be this star. And what star is that? That is Scope. No, that's me. That's the telescope. What star are we on? That's Thalmane Prior. Yep. Yeah, I can't select it apparently because I'm. Yeah. I believe it's that star. Yeah. That's Thalmane. That's Thalmane Prior. All Thalmane 1. And that's Lambda Aquila. Lambda in the Eagle, the constellation of the Eagle. And now, the wild duck cluster, Messier 11, is right here. So we have that. Hold on one second, Daryl. I'll be right back with you.
Okay.
No, I had to give some batteries. I had to give batteries to get the thermostat working again. The thermostat stopped working, and so you're kind of right. The remote stopped on the thermometer, couldn't read anymore.
Huh.
All right, so instead of just looking at this, let's take a picture. And we don't need to take 2 minutes here. Let's go. We can go back down now to 15 seconds, and we can actually try this at 4,000. Let's see what that looks like. What do you say?
Sure.
Sure enough. And where are we? At the wild duck cluster. This is a cluster that's really, really rich. It doesn't look it when you first look at it. And more stars just make themselves apparent. And look at that. Isn't that beautiful?
It is.
Yeah, I need to...
Like a lot of red stars in there.
Yeah. Well, we're actually using... we're using the filter as well.
Uh-huh.
And I think we might need to refocus a little bit as well. This is a good cluster to do that with. So I'm gonna go refocus real fast. I have a focus location. Okay, and let's see. First of all, let me get this going here. Yeah, let me get that. Okay, now let me move this down here. Okay. Go to the east a little bit. And bring this down into the focal zone. Yeah, this is what I'm trying to do here now is just get the stars to focus. Okay. Let's do this now. Alright, so now let me just focus this guy. Get him focused in here. And we'll drop him down. Okay. I'm thinking maybe that looks good. Let's try it. And turn off the focal mode. Yeah, that's better. Look at that. The wild duck cluster. It looks beautiful. Looks wild.
Right.
Yeah, it's really pretty.
It is. Very
Yeah.
pretty.
Yeah, and you'll notice there it does seem to have stars of different colors, and most of the time when you look at a cluster of stars, they're pretty much all the same age, and that's probably the case here as well. But because the cluster is also intermingled with other stars that could be nearer or farther from us, it'll look like the cluster is made up of multiple types of stars at different ages, and that you pretty much never have that in the universe. Whenever you have a cluster, it's born. There's not stars in the same group that are born over billions upon billions of years in the same location. The universe is always moving. Things are always orbiting the galaxy. Galaxies are always orbiting other galaxies, and in billions of years, you'll see that there's movement like that takes place on these gross scales. You've heard Daryl talk about the Great Attractor and the fact that we're all heading toward the constellation of Virgo. Well, we are heading toward the constellation of Virgo, and it's something that is a location where the center of mass of the gravitational forces that are pulling us are located at, and that's where we're heading. Kind of toward Messier 87 in a sense, which is where the black hole was discovered that we saw, the supermassive black hole, the SMBH, which I think we've talked about before on SkyTour Radio, Daryl, I believe.
Oh, yeah.
Look at this.
Yeah, I'm still waiting to. They promised an image of Sagittarius A star too, and I've never seen it.
Well, you got to keep in mind that what they're doing there is they're actually. You got to understand that they're taking pictures long term. Remember, that image was a 10-year image of the Sagittarius A that we saw before, if you remember.
Yeah.
With the stars orbiting. Okay. Well, now with the Event Horizon Telescope, they have to get all this data from the Earth's rotation. They have to get all this. I don't know how long it took to put together the Event Horizon imagery to show us that M87 black hole. But for whatever amount of time that took, they're going to need an equal amount of time at the very least to generate this other one, to do the one for this guy.
Yeah, and the one at M87 was like petabytes of information, I believe.
Oh yeah.
Processing time took longer than the imaging did, probably.
Yeah. I'm going to do 30 seconds at 4,000 here on this M11 again. That is the wild duck cluster. Okay, are we folks talking about the image here?
They were talking about 3 stars in a triangle to the lower right, I believe. But I'm not sure which ones they're talking about. I think they said there were 2 red ones. Maybe right there, yeah. 2 red ones and a white one.
Okay, these guys?
Must be.
Yeah. Could be, yeah. But with pareidolia, you could see a triangle almost everywhere you look.
Yeah.
I'm happy to leave the spring sky behind, guys, because this is just beautiful. And, look how this cluster here is almost invisible to your eye unless you have a big telescope that you're looking in. You'll see a few of the stars, well, like, here. See, here's couple of the stars in the middle. In fact, those 2 stars right there might very well be the stars they're talking about. Let me bring this up a little more. Those might be the 2 right there. Yeah. Yeah, these are good. These are good. Again, these images will all be available to you at their highest resolution that the camera's produced. And you can take them from the SkyTour LiveStream Facebook site and use them for whatever you want. Just let people know they're the SkyTour LiveStream imagery. That's all. That's all I ask. Well, thanks, TP Seeker. I'm very happy you like them. It helps to know your way around the sky just a little bit, and to know what would make you feel, pretty excited about seeing. And I think that what we're looking at here is pretty cool. It almost looks like a globular cluster, doesn't it? Like Messier 13 did. But it's not. This is actually just a fairly tight and young cluster. These red stars, these interlopers here, are probably, again, they're in this galactic disk area, and this cluster happens to be superimposed on it one way or the other, and on those stars. And for a better image of that, we can come back to our view here for a moment and notice that this wild duck cluster right there is amid this entire starry cloud. So the wild duck cluster is going to be, superimposed one way or another on this. And this is a cluster that's over almost 6,200 light years away, almost 6,200 light years away. And the center of the galaxy down in this region here of Sagittarius, is actually on the order of about 22,000 light years away. Actually, it turns out we're closer to the center of the galaxy than we thought. Oh well, what's 10,000 light years, Closer to the supermassive black hole, the center, whatever. Just kidding. Anyway, that's really pretty. It's really hard to just leave some of these objects behind, I wanted to see them all. What do you got? You got some ideas here, Daryl?
Mark, I'm running out of steam. I'm going to have to go for the evening, I think. I hope you'll excuse me.
You hope? Well, of course I will.
Okay. Well,
not a problem.
Been fun. Great night. Saw some neat stuff.
Yeah. It's great, man.
Thank you for having me on.
Sure. And you know what? Daryl, thank you for coming on. And
sure.
We'll talk again soon. And I think we're going to be doing a SkyTour radio this weekend. I just have to write it. Okay? If you've got any ideas, let me know.
All right.
And I'll be happy to implement them. All right, man.
Okay. Well, you take care. Good night, everybody.
Okay. Good night, Daryl. Thank you for joining us tonight. We'll see you later.
Oh, sure. Good night. Right. Good luck.
All right. Bye-bye.
Bye.
Okay. So, I want to look at a couple of the planetary nebulae that are out here. And I'm going to try... I'll try this one. It's actually pretty faint, so let me try this one. Alright, we'll try this one. When we look at planetary nebulae, many times what we've talked about and what you've seen is that planetary nebulae will literally they'll literally look like they have this little, like a blue dot, and they typically do, This is Caus Borealis, the star that we're lining up on right there. Okay, and after Caus Borealis is centered up, it's going to take us over to our target object, which is this little tiny new general catalog, NGC 6629, Planetary Nebula. And so the color they have, that blue, is related to the way in which stars that are around the mass of the sun end their lives. And those stars typically will end their lives by swelling into red giants and then slowly shrinking down to white dwarfs. In the process, as they start to run out of fuel, they gain some fuel, they expand, then they lose it and they contract as the force of gravity wins out over the outward radiation pressure. And then they do this, they pulsate sometimes. Every time they pulsate, they sometimes puff off outer layers that keep going out into space. And that forms these shells around these stars that we see. And those shells become what we call planetary nebulae. And these planetary nebulae will have this characteristic color that starts with this bluish color, this bluish teal color. But let's take a look, see if we can see it. It's a magnitude 9. Actually, I went 30 seconds. I probably didn't want to. I probably only wanted to go a few seconds, because you don't need to go 30 seconds for something like this typically, but we'll do it. And we'll see what we get. Oh, that's interesting. I just noticed in our image here, look at that. 1, 2, 3. You know what those are? They're not UFOs. Those are satellites. And you'll say, well, wow, 3 of them. Yes, those three. Oh, we got the dome in the way a little bit. Ah, that's too bad. But there's the nebula right there. And it's the promised blue color that I had mentioned too. Where'd it go? Here it is. See that? Yeah, it's really cool. Really small, but but that blue color is due to the element oxygen in the star's atmosphere. And the oxygen gets ionized twice. All right, doubly ionized oxygen. And when those electrons recombine, they give off this characteristic light, which together forms this bluish green view, this bluish green look. It's amazing, isn't it? Okay, so I see that the dome's in the way for this guy. So I'm gonna try and see something here. Let me see if we're gonna have trouble if I try to get us to something else that I like, that I know you like. This could be trouble. I'm always causing trouble, guys. What can I say? Okay, I know I'm always causing trouble. That's all right. I don't mind causing trouble if it's so you guys can see something cool. I don't mind. All right, let's see now. Okay, this is what I wanted to show you. All right, let's see where this goes. Let's see where this takes us. We may have to move the dome. If we do, we do. But we'll see. Not sure. I may not. Well, let's go back here. Let's go back. Yeah. This is my favorite pair of stars. We just saw it disappear because we're heading to the object. That was Alberio. That star is an orange star with a blue star with it. And that's a beautiful pair. I got giant hands. That's a beautiful pair of stars. They are a binary star. That star we just saw there. And right here in the middle is the target object we're looking for right now. And I'm going to just do a quick shot at 6400. And we'll do 30 seconds. And we just got to let the guider haul onto a star. and connect. And once it does, we should be able to be okay. I think you'll appreciate this view. You will actually appreciate this view. Because you guys are awesome. There we go. We're going to do 30 seconds at 6400 now. And again, we're using the filter that's going to highlight this oxygen in the nebula. We are looking at a planetary nebula, yes. Okay. Let me also bring back our... not that. This guy. Here we go. So here you can see where the telescope's pointing. You can see that it's actually pointing up. Told you this was going to be beautiful. Look at it. Look at that. Wow. Okay, this is the Dumbbell Nebula. You know, now this is the kind of thing that when you look at an object like this, okay, you can't help but to notice the exquisite structure. All right, like when we look here, okay, first of all, right there, this right here, that's a white dwarf that's inside this. Okay, this white dwarf is the remnant of the star that once was, and we don't know what star it might have been, but we know it had to be a star that was around the mass of the sun, because any bigger than that, and then different things happen up to a certain size. Then instead of white dwarfs, you get neutron stars or black holes beyond that. But this, let me move myself out of the way here. This is the Dumbbell Nebula, and when you look at, you see this beautiful red fringing down here. We see this beautiful red edge here. This is the oxygen I was telling you about. You know, we have helium, we have hydrogen, helium, okay, and we have nitrogen, we have carbon that's created, we have oxygen that's created in the atmosphere of a star sometimes. And sometimes stars like the sun will have oxygen from the previous stars from which they themselves are made. And that material in the outer atmosphere of the star isn't fusing. Okay, when you look at a star like the sun, you think that the whole thing is making hydrogen into helium. Not true. It's only the tiny core where the temperature gets hot enough. In the case of hydrogen, it's 13 million Kelvin. Okay, it has to be high enough to actually take hydrogen and allow the crushing of two hydrogens together effectively to make helium. It's a more complicated process than that. It's hydrogen and deuterium and an isotope of helium, blah, 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 blah. But in the end, you get helium from hydrogen atoms. All right. And that's in stars like the sun. And sometimes that actually occurs, well, we know in most cases that occurs right in the middle of the star in the center. Everything on the outside is all the stuff the star was made with. And it adds mass to cause the reaction deep in the core. But it's not undergoing any reaction itself other than to be turned into plasma, which is stripped of its electrons. Basically, the atoms are stripped of their electrons, and they're just nuclei of atoms racing around with electrons. A lot of this stuff streams away from the sun, and it's called the solar wind. And the solar wind is indeed a case where the sun is actually losing its mass over time. And in fact, it's a well-known process we call mass loss. And when a star is near the end of its life, like it was, it would expand. Right? It started life as a small nebula, and then when it would expand, it would make these shells would slough off, and as they slough off, then they would expand and expand and expand, and the nebula would get bigger. And meanwhile, the star in the center, this white dwarf up there, is so hot that it actually ionizes the material all around here. And this material is something that is going to be very what's the word? It's going to be extremely rarefied, meaning that there's not a lot of atoms per cubic centimeter. All that means is that the radiation will have a great effect on it. And so the electrons jump off and leaves just the nuclei of the, say, oxygen atoms. And then when those electrons recombine, when they just bump around the other things out there and then fall back into the oxygen atom, they recombine and give off this characteristic greenish blue glow. And that's oxygen. Now, with our new spectrometer system, which I have sitting right over there, which you can't see because it's on a shelf, we're going to be able to look at any location in this nebula. And we'll be able to say, okay, what's going on here? What's this made of? What is that element? And we can actually identify everything going on in the nebula. And I can't tell you how much I'm looking forward to that. It's just amazing. Maybe we'll do that with the SkyTour East instrument and leave the SkyTour West instrument as a instrument to just do what we're doing tonight. And let the spectroscopy, we'll leave that maybe to SkyTour East. So we'll have two instruments that do the same relative thing, but they have different capabilities each. That might be pretty cool. Then we'll have a really powerful set of observatories. I think I just came up with that right now, and I think that's going to work. Holy cow, I like that idea. But this is the Dumbbell Nebula. It's beautiful, and I just can't get enough of it. So let me see where we are here. That was 30 seconds at 6,400. I'm going to drop it down to 4,000, and let's do a minute. Okay. Oh, that's actually going to be 2 minutes now. I'm going to change that. I don't want to do 2 minutes. All right, so we go to bulb shooting and take that down. We did a 2-minute shot earlier tonight, remember? Okay, 1 minute. There we go. So 1 minute and close. All right. So now we'll do a 1 minute at 4,000 on the Dumbbell Nebula. It's a bright nebula. And why would we increase the time but lower the ISO? Are we getting anything? And yes, we are. We're actually getting the most amazing increase in or decrease in noise. The higher the ISO, the more noise you get. So we want to kill that. We want to get rid of the noise. Kyle, I see what you said about the Starlink satellites possibly being the cause. But I think I know what the satellites were that were going over. You notice there were 3 of them in a row. Not a row, but kind of in a triangle relative to each other. And while that's taking the picture, I'll show them to you again. Where was that? Where was that? Which image was that? Was that this one? Was it this one? Yeah. Okay. It's measure 11, and you'll know. Come on. Okay. This is my 1 minute shot. Sorry. Look at that. So now you can see it looks so much better without noise, and we can get rid of all that speckling, which aren't stars. The stars are these whiter things. The speckling is noise from the sensor, which we can get rid of. Yeah, but it's really, really pretty. But let me just go back to this for a moment to show you something. Okay, these 3 satellites that we see here, 1, 2, 3. You go to the front of every one of them. Okay, that's where they are relative to each other, and then this is just it's the dragged out light of them. This particular set of 3 is part of a Navy project I happen to know about, and it has to do with ranging stuff on the ocean surface. So 3 of them together are used for this process because they can actually see in stereo effectively with redundancy. So these 3 objects, I believe, are that satellite cluster. I see them a lot, actually. I see these 3 a lot. You see 2 near each other like this, and you see 1 behind. That's the formation that they're orbiting in. All right, and they're at slightly different orbits. These 2 are at slightly different higher orbits. This one's, I think, a slightly lower orbit. Not sure. Don't remember that. But I thought I would mention that because Kyle Lynch mentioned that it might have been the Starlink cluster of satellites. But Starlinks, they don't come over clustered like this right now. They actually would show up like in the view, like say one of these streaks, and then you'd see another one a few minutes later. Initially, when they're first released, you'd see one right after the other. Boom, 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 boom. Because they'd be right behind each other. It wouldn't be parallel like this to each other, like that. But anyway, that's a really cool picture. I'll try to remember to grab this one and make that available to you so you can have fun with it if you like. It's a lot of fun. So anyway, where am I? Oh yes, I'm over here. Let me go see now where I'm going. Okay, so we did our shot here. This shot actually. All right, compared to the others, okay. We have this shot, and then this is the latest one. Right, we see more detail in here. This is, I mean, look at that. I mean, that is just got a lot of detail in it. And it's really, Dumbbell's really pretty for that, just beautiful. Boy, let me see here now. Let me go to. Let me go over to this now. Okay, here we are. Okay, so let's bring this up here. That's the Dumbbell. Yeah, I gotta just. I know that I have a problem with the Ring Nebula. The Ring Nebula, the database is wrong in the Ring Nebula. So it's always a pain trying to get that to show up. And this is going to be out there, but can we actually... We might be able to see this. Yeah, I'm going to see if we can see this. We'll try. Let's take a look at the eastern veil if we can. Okay, here we go. And the stars disappear as we start to track. And let's see what we've got here. Well, I know the telescope's moving, but I don't see it moving on our view over here. It's odd, but, you know, is what it is. Claims it's there. Let's go see. Yeah, sometimes if it's blocked, and as you can see in the view here, it looks like it might have part of it blocked by the dome, which will not be a problem once we are in Arizona. Let's do 25 seconds, and we're going to pump this up to 12,800. Okay, we'll try it. And I'm not sure if we have our guide star yet, but we're going to give it a shot. Oh shoot, I missed Kathy for a second. I'm sorry, Kathy. If you're still there, have a good night. But it's on the stream, knowing that I apologized. Oh yeah, dome's in the way. Ay. Yeah. Okay. Well, it's sort of an ignominious end, but what I'm going to do is, let's see what the sky looks like. Yeah. The Milky Way is past peak already. Those clouds have been lingering up there all night long. Man, I really feel bad for the people living under those clouds if they want to, you know, look at the sky. You know? That's odd. we seem to have a light haze here. All right, well, in any case, I do want to say to you guys, I want to thank you guys for coming out. We are going to call it a night right now because I have to get up early tomorrow morning and work on a Navy project. But I will be back, as Arnold Schwarzenegger says, I'll be back, you know, that kind of thing. And I will make sure that we check out other objects. The comet, by the way, which I thought we were going to be able to view tonight, I had the telescope pointed at the comet location, and in a short amount of time it actually went behind the trees. So as you can see in this view here, we have a pretty clear location, but the actual location of the comet I'm going to show you in this view if I can. Okay, let me see here. Yeah, I can show you. So this is where that tree right there, the comet's going to be right here in between those two trees at its highest, and when we can view it. So we'll get about maybe a half an hour to an hour of viewing the comet. But we'll take photos of it and everything, and of course I'll make them available to you. I might also put the camera on a tripod and just take some exposures, or mount the camera on the back of the telescope and guide with a telephoto just to try and get some shots of the comet as well. So there's promise here, but that won't take place until July 20th at least. All right, and it's going to be around until the end of July at least. So, and it's going to be getting higher and higher in the sky. Tonight it was like in here, right where my cursor is, right down here. It was down in here, and over the next several nights it's going to be up here and moving this way. Okay, actually moving that way. So it's going to be kind of going like that. So when it gets to about there, we're going to be able to see it pretty well, and we're going to look for it as well and take pictures of it. All right. So that said, I'm going to sign off for tonight, and I look forward to seeing you guys again. And you guys are wonderful, you know, and I want to thank you for spending time here at SkyTour LiveStream with me, and of course with Daryl. And let's send our best to Amanda, who wasn't feeling well tonight. And we'll see you next time on SkyTour Radio on Sunday night at 8 p.m. Eastern Time. I think we'll have a good time. So thank you for enjoying the summertime sky with me, and I will be seeing you soon. All right? You guys have a good night. I will talk to you soon. And remember, if you go out, keep looking up. See you later, guys. Thank you.